So thank you everyone for joining us in today's session. My name is Brian, and Lisa and I are excited to host you for this inaugural quarterly executive salon of Refashioned Ventures. Just a few things as we get started. If you want to be speaking in the near term, please mute your mic. I'll leave it to you to decide if you want to leave your video on or not. And since one of the things that we're trying to do with today's session is to start the process of building a community, you're welcome to connect with one another in the chat. So very briefly, I'll tell you about the two communities that we're building. I'll tell you about Refashioned Ventures, and then I'll tell you about our keynote speaker today, who I'm very excited that you get to hear from. So the Worldwide Supply Chain Federation is a network of grassroots driven communities, which we started building in 2017. And the goal there was to hear from people at the grassroots level of companies. So this is a bottom up perspective about the issues that they're facing in terms of sourcing innovations for the work that they do in supply chain and operations, and using that as the basis to try to figure out which startups which are building these innovations are on the right track. Um, and then Refashioned Ventures is a venture fund that is investing in these innovations at the early stage. So these are seed stage and pre-seed and Series A companies who typically say they are building a new innovation for supply chain operations, but it's not always clear if you don't know the industry very well if they'll succeed or not. This community that we're bringing together today for the first time is designed to hear the perspective from the top down. So C-level executives, senior executives, mid-level executives who are not necessarily doing the work directly, but who are responsible for looking for these sorts of innovations and deploying them in their companies. And obviously, Warren, our keynote speaker, represents the builder or an example of one of the builders of these sorts of innovations. So on that note, I'll talk about why we do this, why we are interested in getting the perspective from both ends of the spectrum, from the top down and from the bottom up. The goal is specifically to figure out two things. One, what are the problems? Two, what are the innovations that work? And then to build a bridge between the people who want to buy these innovations and the people who are building these innovations. Today's session is all about decisions, decisions and uncertainty. And Warren will get into that once I stop running my mouth and then turn things over to him. I'm extremely proud that we get to introduce you to Warren's work. I first met him in August of 2016 when a colleague of mine and myself spent the day at his lab at Castle Lab at Princeton University. And he was kind enough to tell us all about the work that he has been doing. Warren has taught at Princeton he taught at Princeton for 39 years. He's the founder and director of Castle Labs. He brought in $50 million in funding from industry and government agencies, and that financing enabled his work in a wide range of dynamic resource allocation problems. Three things to note about Warren. He has 250 publications and 2 books. He's working on his third. And these books are centered on the development of models and algorithms for problems involving decisions under uncertainty. He pioneered high dimensional approximate dynamic programming for problems in freight transportation. And that work was the basis for award-winning projects in truckload, trucking, and rail. And third, he also discovered a universal framework that models any sequential decision problem and has identified the 4 classes of policies that cover every method for making decisions under uncertainty. This work is laying the foundation for a new field, which he's calling sequential decision analytics. Warren, on that note, I'll turn things over to you.
Thanks, Brian. All right, so let me get through the mechanics of sharing my screen. Okay, gosh, normally this is obvious. And I'm not.
Here, let me take a look and see if I need to do anything on my end.
I don't seem to be seeing the screen that. Here we go. Okay.
Great.
And that. Okay. Wow. And I seem to have come in at the end of the talk. There we go. That's much better. Okay. Thank you. I really appreciate everybody coming. Special thanks to Brian and Lisa for organizing this series. So I'm the Chief Analytics Officer for Optimal Dynamics, which is a startup that launched out of work that I did in my lab. I'm a professor emeritus at Princeton, where I taught for 39 years, which was where all of this work came from. I'm going to start off giving you a sense of sort of the diversity of problems that I'm thinking about. And life is complicated. We have our freight transportation that moves things. We have manufacturing that makes things. We have materials handling and supply chains. We have e-commerce and finance. But we also have health and energy. And the range of systems that where we involve decisions under uncertainty is really ubiquitous. It covers sort of everything having to do with human society. And through all these systems, we have decisions, but we have decisions that we have to make in a dynamic setting under uncertainty. So behind all this is the flow of information and decisions. And we don't see this. This isn't like trucks and trains and planes and machines moving around. This is the flow of information. And invariably in the flow of information, we have people. And we have people processing and interpreting and making decisions. Now, at the end of the day, what we want to do is we want to do better. We want to get better performance. We want to reduce costs or increase profits. I want better public health. I want to increase the yield of a batch of drugs. I want to improve customer service and employee retention. And I want to reduce that carbon footprint to deal with climate change. How do we do better? First of all, we do better by making better decisions. So first step is, what decisions are you making? Now, this is where I would love to be in a room where I could see everybody holding up their hands. How many of you in your life, sorry, I can't see you, so I can't actually see you do this, in your professional work, actually have a document summarizing the decisions that you make or the people underneath you? I mean, if you're going to do a better job, you have to make better decisions. Do you know what decisions you're making? And then once you've identified those decisions, how do you make effective decisions? And this almost sounds like, gosh, it seems like we need to turn to artificial intelligence. Now, I have to explain, artificial intelligence is an umbrella term. I see a lot of people in industry misusing this. If you go to a good computer scientist, the first definition of artificial intelligence is making computers behave like humans. And the idea is that if you can make a machine behave like a human, that's the pinnacle, that's the best. But more recently, we're starting to say, wait a minute, maybe I can aim higher. I actually want my computers to be smarter than humans. Now, if you go back to the 60s and 70s, AI was rule-based. If you're eating meat for dinner, then drink red wine. If you have a male patient over 60 with high blood sugar but was not a smoker, then give this treatment. And the problem with that medical application is you get so many attributes, you get so many permutations and combinations, it just explodes. And by the 1980s, it was just dying. All the hype sort of failed and people said, oh, AI failed. Now, I will have to note, we still use rules. In the 1990s, in the decision space, there was this big surge of optimization, and there were really genuine breakthroughs in tools known as linear programming and integer programming. And the thing is, this has some major successes that I'll come back to. But then people started to do things like trying to optimize a supply chain. And that didn't go well because supply chains have all that thing with decisions and information. And the tools in the 1990s was for, you give me perfect data, I'll give you a perfect answer. Now, 2005 was the early days of the new AI, machine learning, and especially neural networks. Suddenly there was this major breakthroughs and everybody got all excited again. Now, what's starting to become known, we're sort of in the early foothills, is this field called reinforcement learning. Now, this is the technology that computer scientists have developed. They can play chess and the game of Go and optimize robots. This is where they're first starting to say, wait a minute, the computer can do better. But reinforcement learning has its own limitations that I'll highlight later. And so what we're doing is looking at the 2020s and going, wait, what's next? And I'm going to say, what's next is sequential decision problems. This is where we need to make decisions over time, but as new information is arriving. Now, there's 15 distinct fields that deal with dynamic decisions under uncertainty, but I'm going to pull these together into a new field that I'm calling sequential decision analytics. Now, I'm going to go through the elements of this talk. Right now, I just want to highlight what I'm going to end up with. That last bullet, the educational program. At the end of this, I'm going to challenge everybody listening to this presentation to recognize that the universities are not producing students with the skills that they need for these complex problems. We need a new educational program, and I'm going to pitch to you that we need industry in particular pushing universities to say, hey, universities, you're not giving us the skill set. We have problems to solve that you're not training students with the tools. But let's go ahead and start with our 5 layers of intelligence. Now, the 5 layers of intelligence, at the very top is decisions. This is the highest layer. Now, people may say that there's some higher ones of creativity, fine, but I'm going to get up to decisions. And we're going to call that the highest, but you can't deal with decisions unless you deal with all the other layers, beginning with the bottom layer, information acquisition and storage. So here we have all these technologies, keyboard entry, barcodes, RFID, GPS trackers, increasingly image sensing and voice recognition and handwriting recognition. These are the tools that are comparable to touch and feel and smell and taste for the human being. Now, when you sense this, you got to bring this data in and store it somewhere. So we have this amazing of data storage technologies. But increasingly, this is just being translated to the cloud, where data comes in and it gets stored somewhere and we don't really care where. And we have to recognize the power of these database tools that allow us to access and manipulate and work with this data, these massive data bases in the cloud. Now, the next stage, once you store all this data, is communication. You're going to have to share it. So we've had the evolution of communication. I'm not going to go back to the very earliest days, but let's go back to payphones and CB radio. But then we had the internet. Qualcomm came in with satellite communication for trucks, cell towers, Wi-Fi. Now we got SpaceX putting up the Starlink network, where we'll be able to have sort of infinite Wi-Fi everywhere. And of course, the smartphone, we have to realize the utter game changer this is, this ability to reach out to pretty much almost any human being anywhere and send them a message and talk to them. Now, even that's not quite enough. So we've got this whole evolution of visibility platforms, and this is very active. So companies like Project 44, if you're a supply chain, you need to know, where is my package? And companies like Project 44 are reaching out and saying, the information is known, it's just not easily accessible, so we're going to provide the surface to pull it together. And so whether it's on this container ship or a boxcar or in this truck, we'll let you know what its current status is. And I have to mention security, just because once you pull all this information together, security is going to be a big deal outside my scope. So I won't touch up much on that. Now, you'll also hear about Internet of Things. This is coming out of computer science. Computer science loves these buzz phrases. Everything we're talking about falls under this massive umbrella called Internet of Things. Basically, we want to know where everything is in the world, or especially where everything is in my supply chain. And then we want to manage it. The IoT crowd doesn't deal with problems of the complexity that I'm going to talk about today. It's just that when people say Internet of Things, just nod and say yes, we're already doing that. Now, the middle layer is the big one. This is the first real plateau where we start doing things. This is ERP systems and transportation management systems. These are the systems that do accounting and billing and order tracking and inventory management and driver tracking and load management. Now we're actually running companies. However, behind all these software systems are those rooms full of people, processing data, interpreting, and making decisions. But this is at the point at which, okay, now I'm really actually running a company. But we're still trying to aim higher. So the next level up is learning. And why do we learn? Anytime you talk about learning, you're in a situation where we have information you know, and you need to estimate something that you don't know. And that's the basis of machine learning. And so things like, how will the market respond to price? I know the price, but I don't know how the market will respond. How long will it take the order to arrive from China? And how many people will need hospitalization for COVID? I've got a batch coming from the supplier. How many of them will meet specifications? And by the way, down in Texas, they at least should have been thinking about how many of these gas turbines will survive that cold snap. Now, you can divide learning into 4 broad classifications. Pattern matching. Is this a flower? If it's a flower, what type of flower? Here's somebody logged into the internet. I know who he is. Oh, by the way, given his purchasing history, I'm going to show him an ad for sunglasses because he might want to purchase sunglasses. Inference. If I change my price, how will the market respond? And what is the condition of a piece of equipment? This is where I'm inferring the state of the world from observations I have. And then there's the good old prediction into the future. I want to know what will the demand be and how many loads will the shipper give me in the future. And what I have is what they've done historically. So when you do machine learning tools, the statistical models that people build fall under 3 big umbrellas: lookup tables, parametric models, non-parametric models. This covers everything. Anybody who comes in and wants to say something about machine learning, you can say, oh, well, what do you like doing? Lookup tables, parametric models, or non-parametric models? Now, you may be saying, wait a minute, whoa, where's neural networks? Yeah, here's neural networks. Neural networks sort of fall in the intersection of parametric and non-parametric. Basically, the smaller neural networks, the shallow ones, are called parametric models, and the deep neural networks are non-parametric. But basically, those 3 circles cover everything. And if you want to do anything with machine learning, you've got to choose among those circles. Now, neural networks, let's just take a second and touch on this, because the big breakthrough with neural networks is pattern recognition, facial recognition, voice recognition, handwriting. These are complex, high-dimensional problems, and they're deterministic. You know, when I write a word or say something, there's only one correct answer for interpreting. Whereas if I say what's demand is a function of price, day by day, I could charge the same price and get a different demand. I mean, a really different demand. And that's what we call stochastic. Neural networks struggle with the random stuff because neural networks are so flexible. They're so powerful. I mean, think of a rubber sheet that you can spread over anything, that they'll have a tendency to try to map the noise. Now, with pattern recognition, you've got to have a label. You have to have somebody saying, oh, here's an X-ray of somebody. Do they have cancer? And what you have to have is hundreds and hundreds of thousands of images where some doctor has said this has cancer, this doesn't, or images and whatnot. You have these rooms full of people labeling these because there just isn't any other way to do it. So it requires a lot of data. And again, the technology is very vulnerable to noise, and the neural network people are not being completely honest about this. We're ready to do decisions. Take a deep breath. This is the top layer. Now let's go back to this complex set of problems. Now behind all these problems, in order to do better, are decisions. And here's an example of all the decisions that will be made. So what we have to do, the first exercise, is identifying all the decisions. And this is an exercise, but if you look at every one of these boxes, you will see decisions to be made. Now, you can divide decisions into 3 broad buckets: physical decisions, financial decisions, and informational decisions. Physical decisions, managing inventories and people and equipment and nurses and energy. Financial decisions is pricing and financing inventory and signing insurance contracts and that sort of thing. And informational decisions is sending information to other agents and running experiments, setting performance targets, doing marketing and advertising are all informational decisions. Now, there's three different broad time frames: the strategic planning, tactical, and real time. Strategic planning is when you're simulating operational decisions to make decisions like how many nurses should you have next year, how many drivers, which suppliers should make each part, where should you locate your facilities, and how big should they be. Tactical planning is when a little bit closer in, does the trucking company say yes to a load now that has to be moved a week from now? Or do I place an order now from China that will arrive in a few months? Or what pricing and marketing strategy should I use for the next quarter, given that sales are down a little bit right now? And then the real time is execution. What driver to put on a load, what bid to put on an ad, what drug to prescribe for a patient. Now, the strategic planning, you can think of, we need to simulate decisions in the future that do not depend on the state of the system now. Tactical planning, we need to simulate decisions in the future that do depend on the state of the system now. And finally, real-time execution is we have to execute. But if I make a decision now, think of a chessboard where I make a move, I have to think about what decisions might be made in the future to help me evaluate the decision now. Now, I'm not going to do math. Well, you're going to see a little bit of math because part of this talk is about the math that we don't have. But here's a piece of mathematics. You may not understand this. There's a lot of people who do, and they're trained in math programming and linear and integer programming. The 1990s, this became a very hot topic. Airline industry. People learn that you can translate airline scheduling problems into this math. And then there's software tools that will say, once you get into this math, I can get an airline schedule. Today, there isn't an airline in existence, major airline, that doesn't work with these tools to do planning. And it's extremely powerful. It was a real breakthrough. Now, you can have simple deterministic planning. What's the best path to a destination? I could do this time-space network for a fleet management problem. This is something Schneider National uses. This is a high-dimensional problem. Now, I'm planning into the future just like my shortest path, where I pretend I know the future and I optimize deterministically. The problems that we're focusing on in this talk don't look like this. It's not like scheduling the airline next year. We're talking about problems where we make a decision and then we see information. And then there's another decision and more information comes in. Yet another decision and more information. And the information that arrives after a decision is made is information that wasn't known when you're making the decision. So let's take an example with inventory ordering, where I make a decision to order inventory for now or the future. And then after that is when I learn what the customer demands are. And then I make another inventory decision and then more customer demands and so on and so forth. So you get the sequencing of decisions and information coming in. In my trucking problem, I have to assign drivers to loads, and then I have random demands on the drivers coming in, or maybe the loads coming in or the drivers quitting. And then I do another assignment problem of drivers to loads, and then more information comes in. And trucking companies live with this all the time. In health, I may make a decision to vaccinate. I have to choose what dosage, which people. Then I have patient outcomes. How did they respond? Did it give them protection against COVID or whatever? And you again have this sequencing of decisions and information. Finance lives with this. I'm trading assets among different stocks. After I trade, I see changes in prices. Then I do more swapping between assets, back and forth all day long, sometimes at very sub-second intervals. Now, we saw this slide with all these decisions, but just as important as knowing all your decisions is you have to think about the information that comes in after the decision. And so here's this slide where after every decision, here's one example of information for each one of those blocks. And by the way, the simple task of articulating the decisions and information, I think is very valuable, even if at the end of the day, you're not going to use analytics. So sequential decision problems are ubiquitous. It arises in every dimension of human activity. This isn't some arcane thing that you say, well, gee, this doesn't apply to me. This applies to all of us. And by the way, we're all making decisions on uncertainty. So let's it may be that the math gets hard, but the fact is we're all doing it. So let's not forget that. The problem is planning into the future is dramatically harder in the presence of uncertainty. Let's take a problem where I have a decision. That square is what I know now. And let's say I'm buying and selling, and I can buy, sell, or hold. And then after that, the prices go up, down, or stay the same. And then I have more buying and selling decisions and more price changes and so on and so forth. Now, this is a trivial little problem, and it just explodes with astonishing speed. I mean, if you take Wall Street, they're doing this at a sub-second level. I mean, imagine planning an hour into the future, how big that tree would get. So let's talk about how to model these sequential decision problems. Now, let me tell you something. If you want to take your real-world problem and use the computer to help you with it, standing in between your real problem and the computer is a math. And the simple fact is, sorry, you're going to have to do math. Now, if you do a deterministic problem, everybody trained in that mathematics of linear programming and integer programming, they know how to do the math. They know how to write it. Everybody's trained in that. By the way, same thing with machine learning. Sequential decision problems doesn't work that way. We don't know how to model it. You can go hire somebody and they won't know how to write it down. They won't write it down the same way. Some entire fields will not even write it down. They'll say, here's how to make a decision, but we don't actually know how to write down your problem. And I refer to this mess as the jungle of stochastic optimization. And every one of these terms is a field. And there's a book or maybe a whole series of books. These are fields that don't even talk to each other. They each use their own notational systems. Probably in these 15 different fields, there's about 8 different notational languages that are completely different. Every one of these books has their own tool. Think of it as a hammer looking for a nail, sometimes a couple hammers, but all of them limited. The reason why we have all these things, there's such diversity of problems that everybody's come up with a very sophisticated hammer, but those hammers only work on very specific problems like hammering a nail. Neural networks is like a really big hammer working on really big nails. So here's how to write down a sequential decision problem. Now, I like to write it as a triplet. We start with the state. The state is what you know. This is the state of knowledge, or the state of information, and it also means the physical state. Then you make a decision where you change something or learn something, and then you have something new that comes in. This is the new information. Now, every time I make a decision, I'm going to receive a contribution. There'll be some metric of how well I'm doing. And the way you make decisions is with something that we're going to call a policy. And a policy says, if this is the state, then here's what you should do. And our challenge here is, how do you come up with the best policy? Now, all right, this may start looking scary, but let me tell you, hidden here on this one slide, right here on one PowerPoint slide, is all the core mathematics that you need, okay? We have state variables, that is what you know. We have decision variables, which is what action we take. We have the new information that arrives. The transition function is the messy one. This says, if I'm in a state, this is what I know, and I take an action, and then new information comes in, this is my updated state variable. And the objective is to find the best policy that works well on average. And these 5 elements describe any sequential decision problems. These cover every one of these books. And so we can start by saying, okay, students, here's the core mathematics. This is what's comparable to that min cx sub to ax equal b that I showed you earlier for the airlines. Everybody in deterministic optimization knows this math. I'm going to claim this is easy to teach. I can teach everybody this. Now there's some additional elements, but let me start by comparing this to machine learning. Now this is a machine learning problem. What I want to do is come up with a function. Now that function we often call a statistical model. Let's say I'm trying to predict demand as a function of price. And maybe I say, okay, I'm going to fit it with a line. So the higher the price, the lower the demand. And there's many lines. I want to pick the best line. And somebody else may come along and go, it's not a line, it should be a curve, so as the price gets really high, the, demand gets lower and lower, but it doesn't go negative. And so I want to be able to search over these things. And in fact, actually, I need the full toolbox of lookup table, parametric models, and non-parametric models. But if you hire somebody with a machine learning background, they know about this toolbox. They don't come in with just one hammer. They've learned a rich set of tools. Now, you need a data set. X is the stuff you know, Y is the stuff you don't know. Like X is the price, I specify the price, Y is when I observe the demand. And my challenge is to find a good function. And this is what all people with a background in statistics and machine learning do. They have a toolbox of functions, and they usually through intuition say, I think this will be a good function. Increasingly, a lot of people say, oh, I'll just use the neural network. Fine. So let's compare machine learning to sequential decisions. Machine learning, I want the best function, a statistical model. Sequential decisions, I want the best function, but we call it a policy, method for making decisions. Machine learning, I need a data set. This is the world of big data, but if you're doing machine learning, you've got to have a data set of the X's that I know and the Y's, which are the training stuff. This is what you have to get from history or a room full of people labeling those X-ray images. Sequential decisions, you do not need a big data set. You have to be told, here's the cost, here's the profits, here's the performance. And by the way, not shown is that I need that transition function that tells me how the state variable evolves over time. But let's now focus on that issue of searching over policies. Okay, let's drill into this. Designing policies. What's a policy? So it's a word in everyday English, but it means different things to different people. I use it because not only is it a word in everyday English, but the academic community likes it as well. A policy is a method that translates information, the state variable, into a decision. Any method. So how do we search for the best policy? What we have to do is come up with the same type of toolbox that the machine learners have. Now, the notion of making decisions is very rich in the English language. These are 45 words, and I'm up to 45 words, probably there's more, in the English language that all roughly mean policy. Okay, and you can use any of these words. I'm going to stick to the word policy. If you go to tinyurl.com/policies and decisions, you can see the spreadsheet and maybe contribute something that I didn't think of. Now, it turns out there are two fundamental strategies for designing policies. The policy search approach. This is where we're going to look for a class of policies. We want to find the best class, like that linear function or a neural network, and then we want to find the best policy within the class. The other strategy is look-ahead approximations. I'm going to find the best, make the best decision by saying, okay, if I make this decision, I'll earn this cost or contribution. But now, like the chess game, imagine that you make a move in chess, but you think about the downstream moves. I have to approximate that future. Okay. Now, these are two broad strategies. What I'm about to go through is I'm going to get a little bit more specific. Each of these broad strategies can be divided into two classes, creating what I'll be calling the 4 classes of policies. So the first of the 2 classes under policy search, we call policy function approximations. Now, this is going to look familiar to you because in the inventory and supply chain world, let's take an inventory problem. Inventory goes below some number, a little less, I'm going to order up to big S. It's an order up to policy, very common. This is a PFA. And guess what? Lots of our decisions are from PFAs. If you're in finance, you may use a buy low, sell high. You know, there's a point at which you buy, there's a point at which you sell. If it's cold, I'm going to wear a coat if the temperature is below some number. The universe is full of decisions. Most people are making decisions using something simple. PFA is easily the most widely used class. Now, also widely used, but not well recognized, is something I'm calling a cost function approximation. This is a parameterized optimization problem. So simple example, find the shortest path. You use Google Maps, you find the shortest path. That's an optimization problem, but you also have to decide, when am I going to leave for my trip? And Google says it's going to take 40 minutes. And you're like, oh, I don't know. I don't want to arrive late. I'll add 10 minutes. And if you do this trip over and over again, you may find, oh, you know, a couple of days ago, I was late. So I'm going to make the 10 minutes into 15 minutes and hope that that does better. So that's your tunable parameter. Or energy, the energy companies, they plan for tomorrow and they know how much energy they'll need, but they put in buffers. They put in extra energy. Now, Texas didn't put in quite enough because they didn't anticipate how many generators would fail in cold weather. So there was a source of uncertainty that they ignored. Now, CFAs were actually widely used in industry, a very powerful tool, completely ignored by the academics. But PFAs and CFAs are the two classes of policies in the policy search strategy. All right. Okay, I promise you, this is the most complicated piece of mathematics in the entire talk. The thing is, we're going to need it. Now, this is the one where, imagine that you're playing chess and you're going to make one move. That's the contribution you receive now. Maybe I was able to take opponent's piece. And this is the future. All that messy gobbledygook is the future. And yes, it's as bad as it looks. Now, I'm hoping many of you have seen a decision tree. So I was talking to Dirk, who works at Cargill, and he gave me a whole pile of, he gave me the setting of shipping to Nigeria in a big container ship. And he was walking me through all the decisions under uncertainty. So for example, he has to choose the vessel and the departure time, but then there will be delays due to weather and the availability of the vessel. We have decisions for ship speed and currency hedges and which port the ship should go to. And then I have randomness in the oil prices and the currency changes, but I have a decision for selling contracts, but then the product might spoil. So there's this whole mixture of decisions and information that I have to wade my way through. So let's put these two together. Using this decision tree example, we have the first decision. Now, this is the decision I'm going to actually make and implement, but the way I'm making it is to think about the future. Now, the first thing is so this is the state that I'm in. This is what I know now. These are the decisions, which, by the way, there may be much more than 3. Now, I'm going to have something random happen, and because it's random and I don't know what's going to happen, I'm going to take the average. That's the E for expectation. I'm going to take the expected value. Now I have everything else in one giant lump, and that's about as bad as it looks, but I'm going to go ahead and say that letter pi is the Greek letter. That's what we most often use for policy. This is me searching over policies. And the policy is going to specify not what decision I make, it's going to specify the decision I make at every one of those square nodes. And then that inner expectation is the expectation over all future uncertainties. And I'm not going to hide the fact that that part is hard to compute. So what we have to do is now work our way through that. So we have 2 subclasses of policies in the look ahead class. The first one is where we take that ugly function and say, let's just boil it down to, so that's the value of being in a state ST plus 1. And this is all my future contributions, and I can boil that into just a nice something called a value function. So there is a whole academic community that solves problems this way, and there are very special cases that can solve it exactly. It's a tiny number of cases. This is a very little practical value. The mathematicians love it because they prove all kinds of theorems. Now, if you want to make it practical, maybe you do something approximate. So this gets better, but I have to tell you, somebody who works on the computer, that E, normally I tell my students have cold, sweaty palms when you see an expectation. Usually you can't compute it, but it turns out you can get rid of it. Okay, this is my book on approximate dynamic programming, where I said, oh, there is a way to get rid of it. And now that's a deterministic problem, and I can use the tools of deterministic optimization. And by the way, this is one of the foundational technologies of optimal dynamics. Before I illustrate this, let me just mention the 4th line. This is what the computer scientists like. This is the language they use, and they call it Q-learning. And this is in the field called reinforcement learning. And if you haven't heard of it, keep your ears open because it's starting to run waves. Computer scientists are brilliant at advertising what they do. So let me just take a quick little trucking problem where I have drivers and loads, and I have to assign drivers to loads. But finding the best driver and which loads I should move, I have to think about what could happen in the future. Now, remember my earlier problem where I could buy, sell, or hold is pretty simple. Now I've got 1,000 trucks. And I have to decide what to do with all 1,000 trucks all at once, given all those uncertainties in the future. This is gargantuanly bigger than my initial little illustration. But if I use this value function approach, that first contribution is the cost of assigning drivers to loads, and that V bar in the future is just the value of drivers in the future, an approximate value. I got to tell you, this problem is easy to solve. And I can do this we did a test at 100,000 trucks. We have no trouble scaling. And so this was a nice breakthrough that came out of my lab that allows us to say, I can take sequential decisions for a big fleet of trucks and have very practical tools. All right, now let's go back to, so some of the major breakthroughs. If you're a computer scientist, one of the things that they're going to point to is the game of Go. Now, for the longest time, people thought computers are great, they're getting better and better, but computer will never solve Go. It's just too hard. And then they solved it. They beat the best expert. And when I talk about artificial intelligence sometimes being smarter than a human, that's one of the examples. Now, all of you are from industry. Okay, so let's look at the one on the right. This is a fleet of 5,000 trucks from Schneider National. Every truck has a truck driver, has an equipment type. He has a home domicile. He has hours of service. I'm trying to put the best driver on the best load, and I want to get him home on time, all at the same time. And I've got to tell you, I think that's kind of impressive. And so while I acknowledge the computer scientists and playing Go is kind of a cool thing, but I don't know, I just find optimizing 5,000 trucks maybe a little bit more impressive. All right, so now we're down to, but value functions don't always work. And I spent 20 years and wrote a really nice book, and I'm here to tell you, approximating the value of resources of the future, it's a good tool for some problems. And if you were talking to Warren Powell 15 years ago, I'd be beating my hammer. Oh, approximate dynamic programming. I can optimize big trucking companies. I can solve anything. 15 years later has taught me, no. It's a nice tool, and it has problems where it works great. And it's not that many problems. Now, one of the things is this big messy piece of mathematics. Let me tell you about this fourth class of policies. This is what you do when all else fails. And as I like to tell my students, and all else usually fails. So as messy as this might look, this is often where we end up. And I think this is where we're going to eventually end up in the supply chain world. So let me just put it this way. I can't solve that messy equation up there. So what we're going to do is we're going to approximate. We're going to approximate uncertainty. We're going to maybe simplify some of the dynamics. Maybe we simplify some decisions or how we make them in the future and how we make decisions. Now, however it is, and that's an art form, okay? This is where you need people who spend time. But let's imagine that I'm going to peek into the future, optimize to figure out what I should do now. And then I'm going to advance the clock, roll forward, do it all over again. And then I'm going to advance the clock and do it all over again. And each time I make the decision now, it's by peeking in the future. If you want to use the analogy of the chessboard and thinking about what move might be made next, but I can also say, well, let's take Google Maps. So this is an interesting trip because I was up in Hartford, Connecticut, working with Pratt & Whitney on a supply chain project. We'll come back to that in a minute. But this is me at 4 o'clock in the afternoon planning my trip back to Princeton. And guess what Google's doing? It's got this great trip right through New York City. And I'm going, Google, no, you're smarter than that. Now, what Google's saying is, oh, no, that's the fastest trip. 3 hours and 21 minutes. And I'm like, it might be fast, but it might be a nightmare. I've got to deal with the uncertainty of trying to drive through New York City. So here I am saying, Google, I don't like how you've approximated the future. I'm going to do more of a worst case because I'm a little bit risk averse. There's this trip over the Tappan Zee Bridge that based on your numbers takes me 5 minutes longer, but I can tell you there's a lot less uncertainty. So this whole science of looking to the future and approximating the future, these are whole fields of research. Now, if you want to get fancy with your friends and use Google Maps, you can say, whoa, I'm using model predictive control. There is an entire field of research, whole books on model predictive control that are nothing more than looking the future deterministically and say, let's just do a point forecast in the future and optimize and do that. That's called model predictive control, whatever. There's another whole field called robust optimization, yet another whole field called stochastic programming. You can take my book, Approximate Dynamic Programming, and use it as a look ahead, chance constraint. These are whole fields dedicated to certain ways of approximating the future. And so this is all very rich, and there's a lot you can do here. I think there's even more that you can do here as I started to poke at the supply chain area. All right, let's take a deep breath. So we talked about designing policies. I said there's 2 basic strategies, policy search policies, look ahead. The policy search policies come in 2 classes, the PFAs and the CFAs. The look ahead come in 2 classes, VFAs and the DLAs. Now here I'm going to make a pretty strong claim. I claim these 4 boxes are universal. There's nothing else. I haven't left out anything. This is everything that's been studied in any book anywhere. This includes everything that anybody has done in practice. Now, how do you know I make that claim? Let me put it this way. You take a long time before you stand up in front of a group of people and say, this is universal. Let me tell you why this is so important.
All right, so I think people have heard enough.
Thank you, Daniel.
Okay, can I keep going?
Yes.
All right. And so if I come into a company, it's very common for a company to say, oh, we need new tools to make better decisions, and let's hire expert X, either from academia or a consulting firm, and they come in with their special tool. In the 1990s, it was optimization. i2 Technologies was good at that. And what this allows me to do is to come in, and my first question is, what are you doing now? Okay, let's start with what you're doing now, because whatever you're doing now is in this framework, okay? And then I can first ask, can we do a better job using the approach that you're already using before we start pivoting to saying, okay, here are the weaknesses of what you're doing, but if I go to this class, here are what the capabilities are. Now, I've got to tell you, I'm sorry, I'm going to go back here. The look-ahead policies are absolutely more complicated. Guess what? Most of the books on this field are on look-ahead policies, VFAs and DLAs. You go into the real world, what you're going to mostly find is PFAs and CFAs. And I think it makes a lot of sense that people like simple policies in the policy search class are simpler. The CFA class I got from industry, not from any book. But I learned to tell my students the price of simplicity is tunable parameters, and tuning is hard. So we have to realize that when you use a simple rule, buy low, sell high, those cutoff points have to be tuned. And do you tune in the simulator? Do you tune in the field? This is harder, and a lot of people just don't do the tuning. All right, so this may look very technical, but I'm just going to have some fun with you. Please go to jungle.princeton.edu, scroll down until you see this picture, download it, print it out, pin it up to the side of your desk. Anytime somebody comes in struggling to make a decision, just point at this. This is the universal framework. I mean, obviously very streamlined. It has all 4 classes of policies. It has the objective function. I don't know, if you hire a fancy consultant, put this and say, okay, where does your work fall in here? Because whatever they're doing falls in here. Little illustration, an inventory problem, but it's going to be in the form of energy storage. So I've got a little energy system. I can get energy from a wind farm, but it's a variability and very uncertain. I can get energy from the grid, pretty much infinite, but at very random prices. I'm trying to meet the load and demand that varies over time, but I do have my Tesla Megapack battery storage to absorb the fluctuations. Now, what we did was we took this system, we spent a lot of time working on this problem and created 5 different variations of the problem, Then I created 5 different policies. The first 4 of these are from each of the 4 classes, and the 5th one is a hybrid. And the number in the square, the bigger the number, the better, and the yellow is the best. We made each of these 5 classes work best just by changing the characteristics of the problem. And this is why I think students need to be taught all 4 classes and plus be aware of the hybrids that they can build. And if you come in, and right now universities are not teaching this. Universities are teaching people who come out with expertise in one of these classes, and that becomes their hammer. By the way, the CFA class, students aren't even learning in schools. This is brand new, but I got it from industry. I was watching what companies did. And so I think this is insightful, and because this is an inventory problem, it also walks over to supply chain. So let's go back to our how do we design policies. So in machine learning, we have the lookup tables, parametric models, and non-parametric models. It turns out all of those functions exist within the PFA class. Everything that you can come up with as a PFA, it corresponds to one type of mathematical function you might use in machine learning. And these are all analytical functions. It's the simplest class, but the whole field of machine learning fits in there. Just the objective function is different. Otherwise, it's the identical problem. But then we have our CFAs and VFAs and DLAs, which are all themselves optimization problems. And you have to be aware of these. They're very important, but you need them all. This is how we search over policies. So it's like machine learning, but expanded. Now, I have an online book. It uses a teach by example. If you go to tinyurl.com/sequential decision analytics, you can access the book. With the exception of 3 chapters, every chapter is an application. They all use the same outline. They have a narrative and a particular modeling style. The problems are chosen to illustrate all 4 classes of policies. And we also highlight the importance of modeling uncertainty, which is often not given as much attention as it needs. But this is going to be my major book. It's almost done. I have to submit it this September. It should come out next year by Wiley. This will be more graduate level, but this will be comparable to other technical books like Optimization and Machine Learning, and it pulls everything together. So I'm going to note the universal framework covers any sequential decision problem. The 4 classes of policies cover every method that has been suggested for making decisions, either in the academic literature or used in practice. This means that we can always start by modeling how decisions are made now, and then create a path to a better policy. Also, when you choose a policy, you're not always going to choose what is academically the best, because you're going to consider computational cost and data requirements. Transparency is a biggie. Sometimes people really do want to know, how did you make the decision? And diagnosability, if something goes wrong, do you know how to fix it? And these are really important. And transparency and diagnosability are one of the reasons why people sometimes veer toward something simpler, because these are important issues. So let's go to a little bit more complicated problems. Supply chains. Okay, so this is my work with Pratt & Whitney that we did. They have 1,000 components from 600 suppliers, lead times up to 300 days, uncertainty in all kinds of places, product yields, manufacturing times, the production capacity. We put together a multi-agent simulator. And so here's a product moving all around the world for Pratt & Whitney. And you can say, well, wait a minute, come on. This is really complicated. How do you possibly optimize the supply chain? Because, it's just too complicated. Well, the first thing that you have to realize is it's not one person making all the decisions. There's lots of people making decisions, and you have to model every person. So we call these agents. This is a multi-agent system. And what you'll do is you're going to take each agent and turn it into a policy using the vocabulary. So if we think of taking an agent at one place and one vendor, and we're going to model just that one person. Now we'll have other agents doing things that impact this agent, and decisions that our agent makes will impact people downstream. Now we've taken a very, very large complex problem and turned it into lots of much smaller problems. So we built this supply chain simulator for Pratt & Whitney. They are using it, but it's just a simulator. And you're like, well, wait a minute, just building a simulator doesn't prove too much. Let's go to Norfolk Southern Railroad. It's a company we worked with for 10 or 15 years. And we actually built a system. These are individual, we model this over time. We have individual freight yards, and the decision is really made in every individual yard. Just like you have the different agents in the supply chain, we have the different yards making their own decisions. I don't optimize all of Norfolk Southern all at once. I optimize every individual agent. And then I realized that decisions made by one agent have a downstream impact. We use what's called feedback learning. This is from approximate dynamic programming to say, here's the impact. And then by simulating this over and over many times, the agents start to learn to work together. But at no time am I ever solving a problem bigger than one yard over a 4-hour time period. Now, this system is in production. This is an award-winning paper co-authored with the team at Norfolk Southern. The lead was Clark Cheng, who's there on the paper. This system has been running there for 15 years, doing strategic and tactical and operational planning. Clark's still there. Go ahead and call him up, and he'll tell you that this is working. So now I'm saying, look, I've got this multi-agent approach running Norfolk Southern Railroad, running the locomotives at Norfolk Southern Railroad. So now let's take something a little bit closer to home. So we're going to do a brief case study on refashioned OS. So the vision of refashioned OS is, rather than going to Target with infinite racks of clothes all over the place and huge inventories, which is also hugely inefficient. We're going to do clothing on demand. And what we're going to do is have factories here in the US where a lot of the work is automated. You still need some handwork. So you're going to have these sewing circles that do the last little bit that, that at this point humans are better at. By the way, Elon Musk had to go through this learning experience with his automated factories. I love his line, humans are completely underrated. And then, so what they're going to do is have a number of these sewing circles in a micro manufacturing facility. This is a startup. And so one of the things they're going to have to do is to learn how to grow. They have to learn how to plan, how to expand the network, how much growth to plan, when to start construction. And there's a lot of uncertainties in demand, overall demand and demand for individual garments. Now, Lisa's going to have to sit there and plan how her company grows out as the demand unfolds. And so this is a rolling operational plan with a lot of uncertainties. So I sat with her and said, okay, let's start identifying your decisions. And I think this is a fabulous exercise for anyone. I mean, please, if you never talk to me again, go back to whatever it is that you're trying to manage and write down the list of decisions. It's a great exercise. And of course, after you make the decisions, write down your uncertainties. Both what was uncertain when you made the decision and then the information that comes in after you make a decision. So at REFASHIOND OS, they have strategic planning decisions and tactical planning decisions and real-time execution. And so one of the things is it just because you have a decision, does that mean you need a computer? No, this will be like her vision where they'll have machines cutting out fabric. They'll use machines for some actions. You still need humans for other ones. The world for the foreseeable future will be a hybrid. So let's now close with this educational program. Okay, we're going to see a real challenge, and this is where this talk cannot just be entertainment. I need people going off from this and saying, okay, we need to change something. So I showed you this mathematics and optimization. It's widely used. All the airlines use it. It's used in many, many settings. I mean, this is a big field. There's lots of books. They all speak roughly the same vocabulary. If you want to hire somebody in optimization, go to the internet, search. It's not hard to hire somebody. There's many people coming out with these skills. They all speak the same language because it all comes from this one book, George Danzig, written in the 1950s. He invented the field. And so everybody, I don't care what country they come from, speak the same language. The same is roughly true of machine learning. There's many books, but if you hire somebody in machine learning and data science, they're all going to roughly have the same skills. They're all going to learn about parametric and non-parametric models. They're all going to learn about neural networks today. There's a lot of software out there, a lot of it free. So you have tools and concepts. I mean, you need people who have technical training and understand the mathematics, but this is master's level. This isn't even PhD. I mean, there's a lot of people with PhDs in this area, but you don't need a PhD to be a practitioner. By the way, there's a lot of people who are smart enough to teach this stuff to themselves on their own. Now, in these dynamical systems, there's another field called simulation and stochastic modeling, and this is also a field with a lot of books. And if you want a good simulation person, they're out there and they have the training and there's tools, and this is also a well-defined field, but not the world of sequential decisions. This is a complete mess. I was on the phone with a startup doing supply chains just last week. He was saying, who do I hire? And I couldn't tell him because, you know, yes, you'll need people with machine learning, but math programming, sometimes you need it, but sometimes you don't. But you need this whole world of sequential decisions. We're not teaching it. It's not being taught. So I'm going to claim that these two books are a start. Both of these books, one more advanced than the other, cover all of these fields. Okay, it's not like, okay, guys, I have the ultimate hammer, come buy my hammer and I'll solve your problems. No. All the hammers are great. We need all the hammers. We need the toolbox, but we need them organized, and we need students with a background across all the fields, just like optimization and just like machine learning. And so when you go into an application, you never know what tool you're going to need. Right now, academics are being taught by professors who are specialists in dynamic programming or stochastic programming, and all we're getting is people trained in the specialty of that academic. And it's a really pervasive problem. So let's now go take a look at the literature on supply chain management. So I downloaded a bunch of books or images of them, and you can roughly divide the books into two very distinct categories. On the left-hand side of these very theoretical books, I mean, this is heavy math, and most people look at it, you know, from management background and roll their eyes and go, okay, I don't understand a word of this. So I do. I understand everything in those books. I know exactly what they're doing, and it's all toy problems. There's nothing in there that really solves a supply chain problem where you're getting things from China, but you could air freight it. I mean, all the messy stuff that goes in supply chain, those books aren't touching. But let's go to the books on the other side. The other books are great books. They cover issues. They make you understand problems better, but they won't teach you how to program a computer to solve the problems. You won't get analytics, implementable analytics out of that community. The problem we're running into is that the supply chain area is viewed as a business school, the domain of business schools. MBA students, as a rule, are not very technical. These are not the students that you sit down to write code. And the professors don't run big grants like, you know, I ran a lab that ran about $1 million a year with funding from industry as well as government. That's what people do in engineering. A lot of engineering schools do things like that. My lab might have been a little bit bigger, but this is not unusual. The problem is the B school professors have to do something for research because that's how they become professors. So what they do is they take these very stylized problems and prove theorems. And nobody can understand the theorems. And so they go, oh my gosh, this person must be very smart. I'm here to tell you that some of my closest friends are the very, very top theoreticians in this field. They don't know how to model a problem. There's some really fundamental stuff that they don't know how to write down on a sheet of paper. And it's stunning what this field is missing. So here's my proposal. I think we need to establish academic programs in engineering that focus broadly on sequential decision analytics, comparable to programs in machine learning. As with machine learning, this program could be centered on different problem domains. It spans business or transportation, logistics, energy, health. One of these could be centered on supply chain engineering. But we need leaders from industry to push for this change at universities. The tech sector is going to start addressing this. Companies are starting to wake up, and I can tell you the tools aren't there. And so I'm going to close this. Thank everybody for listening. Thanks again to Brian and Lisa for putting this together. I think we are really at the cusp of a new wave of analytics for supply chains and other sequential decision problems, and there's a lot to do. Thank you very much.
Thank you, Warren. Thank you, Warren. This was fantastic. So Dirk and Kara, I'm going to ask you guys to turn on your cameras. And Warren, thank you. Let me do the intro. So I'll introduce Kara and then I'll introduce Dirk. And for people in the audience, this is when you can type in your questions in the chat box, and I'll be monitoring those, and I'll pull those into the conversation that we're going to have with Warren as time progresses, and this should last about an hour. So Kara Yokley is an analytics strategist. She helps companies draw insights from existing data. She's the principal of RRDS Chicago, which is a boutique data science consulting firm. 3 things to know about Kara. First, with her team of PhD data scientists, she has worked with companies as varied as GE, Tenneco, Kraft Foods, and some of the world's largest financial services firms. Second, she's a creator of the MOTO framework. I think I should pronounce that motto. And it's a framework which provides a roadmap for non-technical business managers to direct and successfully navigate complex data science initiatives. 3, as an analytics translator, she excels at bridging the gap between business use cases and their technical implementation. And we're hoping that Kara is going to pose some of the issues that she's dealt with at RRDS Chicago to Warren. Next on the panel, we have Dirk Robers, who's joining us from Cargill. Dirk is a design thinking practitioner with 20 years of experience. Starting out in architecture and urban design, his avid interest in technology and everything related to trade led him to the world of commodities, and supply chains. And as Warren mentioned in his talk, they had a conversation about some of the issues that Dirk has to deal with on a daily basis. Two things to remember about Dirk. After a brief stint at Glencore, where he first applied design thinking and his fascination for uncertainty to design a new integrated system for origination and supply chain management. He developed an outsider's perspective on supply chain and the processes, but particularly the people that make the decisions each day in an uncertain space, trying to make that uncertain space a little more certain. Second, today he manages a team that advises Cargill's many enterprises in APAC, in EMEA, in LATAM, and North America, from structured finance to supply chain and from animal feed to ocean transportation, where he now applies this approach within Cargill, looking for spaces for disruption and innovation and taking the enterprise beyond current and adjacent into unknown and unmet needs. So on that basis, I think I'll go to Kara first, and I'll say, you know, what's the thinking about some of the clients that you've dealt with at RRDS. What were some of your first impressions as you watched Warren's presentation? Is Kara is still on mute? Kara, you're on mute.
Okay.
so Dirk,
Okay.
Dirk
Is
and
that
Kara,
better?
yes, go ahead and
Okay.
unmute yourselves.
Okay, I unmuted my phone, but not my computer, so a little bit of a disconnect there. But thank you, Professor Powell. That was fantastic, and you know, I feel like really an important framework for people in industry to start to structure their thinking. I think one of the challenges that we face when we go in for consulting projects, and I think you talked about this a bit, is that sometimes even the problem hasn't been structured in a way that you can think about actually how to solve it. And so we spend a tremendous amount of time actually helping clients think through what is the actual problem that you're solving, what are the resources that you have available today, what gaps do you have in your understanding and knowledge, computational power, all of these things, right, et cetera. And so these are the major challenges that we face even before we get to the point of actually picking a model and then applying it. So I feel like, you know, a lot of the time that we spend is, you know, I'd say maybe 10% of the time is actually doing data science kind of work, and 90% of the time is spent cleaning up all these, you know, other things. So I'm wondering, Professor Powell, if you have any thoughts on like decreasing the amount of time or getting people in a better position to be able to spend more time higher in that pyramid that you showed of, you know, the learning. So we spend less time in the bottom three, more time in the top two, and potentially beyond.
Well, so the bottom three, we just have to realize, you know, we can talk about doing really cool stuff, but if I simply don't know where something is, you know, that tends to be the showstopper. Early in my career, we were optimizing trucking companies, and gosh, we didn't know where the driver was, and we depended on him. So the bottom three is important, but let's get back to the top. Let me answer your question a little bit more directly. When I go into companies and I want to try to help them, my top three questions tend to be, number one, what are your decisions? I'm the guy who's sort of famous for saying, what's the decision? Because if you don't know what decisions you're making, how do you make it better? Now, when I ask a company, what are your decisions? They'll sometimes say something like, oh, we want to minimize cost. And that's not a decision, that's a metric. And I've learned to sometimes start with the metric and say, okay, tell me what your metrics are. What are you trying to achieve as a first cut? And then once they tell me what they're trying to achieve, and it's not one thing, usually it's a list, okay? Life is complicated. You don't have just a single objective. But then I get to the, okay, so what are your decisions? And generally, they haven't always thought these through. And then the next one after the decisions is, what are the sources of uncertainty? What are the, what goes bump in the night type of thing? And I've had companies say, how do you identify the sources of uncertainty? And sometimes I answer, we'll get a couple 6-packs of beer and sit around a whiteboard and do brainstorming. Figuring out what the decisions are in a complicated problem in a supply chain, it's not just planning inventory. There's a lot of stuff that goes on in an actual company. Okay, so it's not easy. You can have the big things of how much inventory, but honestly, running a complex operation, there's a lot of things going on with people that do represent decisions. Now, sometimes things don't appear to be a decision because they've already fixed the policy. They already know how to make the decision. And sometimes you have to realize, whoa, wait a minute, that was a decision. You just happen to make it this way. So metrics, decisions, and uncertainties are my top 3 things that I like to get a handle on. But one thing is that with the framework, I find that my framework tends to tell me, look, if you're going to build a computer model to solve your problem, this is what you need. Well, even if you're not going to build a computer model, you still need those same things. Now, when you go to make a decision, you're going to need a policy. Usually that starts walking you down the other elements to say, okay, what data do you need to make that decision? And now you start walking down, do I know where the truck driver is? Do I know my inventory? Do I know this? And it walks you into those other pieces of information.
Dirk?
Yeah, so maybe let me start with that final notion, the pack of beer and but that is actually that kickstarted me in this world. Coming from a different industry, having a fascination for technology, and then thinking, how do I apply my knowledge? How do you manage complexity and uncertainty from an urban perspective? So you plan a city or a country, it goes down levels. And then at some point you hit an architect and they have to design, and it goes even smaller down to the screw and so on. And that kind of fascinated me also in companies. So companies make long-term projections and plannings and so on. They kind of, model the people and the storage places that they have and the supply lines that go between them. And then they say, well, this is how the year will look. And now we're going to execute, and the days and so on progress. And you have your medium-term planning in between, and then you have your day-to-day. But there was an apparent disconnect, because each time I would ask, so how do you decide on what you do today, how that relates to what you thought you were doing in the medium term and what you thought you were doing in the long term? They had no clue. So there is no place for capturing that decision. And I was wondering, so talking about going down those levels, just like in an urban situation, when do you stop? How do you model something like this? You can go, everything in, like we said before, is a movement from A to B. In between, there's a movement from A to B. Then it goes down a scale. There's a cost function. It also relates to the A to B. Where do you stop the modeling, and how do you find the correct level?
I think it all focuses on the decision. I keep coming back to the decision. So for example, the movement from A to B, when was that decision made? I mean, because sometimes that decision was made months ago, okay? And you have to go back months to say, okay, well, that's when the decision was made. Now how was it made? Okay, well, that has to do with the class of policy. And then once you sort of have the how was it, and I don't care whether you're making it the best possible decision or not, let's just take how you're making it now. Now, one challenge with humans making decisions, one of the problems with humans making decisions, they often can't articulate how they make a decision. And, you have a room full of people all making decisions. You have a process that cannot be managed. Okay, you can beat on them, you can have metrics, you can give them incentives, whatnot, but you don't actually know how they're making decisions, which means you're out of control of your process. And well, welcome to life. Okay, we're not going to entirely get rid of that. If you get to the more operational decisions, I think the more operational, the more it becomes something very frequent. Those are the decisions where you're like, okay, now I actually do want a computer making the decision. Whereas as you farther into the future, sometimes I want the computer simulating, but to help me make the decision. Like if I was going to help Lisa with her rollout of opening new facilities, I would build a simulator and say, well, if you build a facility here, here's how well you would do versus building it here, and then still leave the decision up to her. So it would still be a human-made decision because she can locating a facility is multidimensional, okay? But the computer can do a lot of the detailed stuff. But I keep coming back to, number one, please tell me what is the decision? Tell me when the decision was made. And I like to articulate, what would I do if I wanted a computer making that decision? Because the beautiful thing once you do that is now you do know how it was made and what information you need. And so I've gone through the school of hard knocks. Not all of my projects have been successful, but every single project, we've learned a lot. And one of my most successful projects was where we said we were supposed to be building this optimization model to optimize trucks for yellow freight. And at the end of the day, the optimization model never actually worked. But to build the optimization model, we had all these supporting systems. They loved the supporting systems because the humans needed it too. But when a human says, I can't do my job without this, a lot of times the response is, well, work harder. And the thing is, sometimes humans ask for stupid things. I mean, sometimes the human says, I need this. And you spend a lot of money on the report, and then they find that they're not actually using it.
Using the report.
Whereas when you have a computer model that says, look, the computer needs this data here, it's unambiguous and it's wonderful. And it's one of the great exercises. This is one reason why I do think learning analytics is a useful exercise, whether or not you're actually going to write code to have the computer making that decision. It teaches you how to think about a problem.
Kara, so
I just wanted to add one other thing, and that is, when we're helping clients think through the problems that they're facing, we have this kind of matrix that we think about, how complex is their data, how structured is it, unstructured, and then how complex are the processes that we're going to be trying to model. Are they rules-based? Are they more ad hoc? These kinds of things. So I just want to throw out that, one of the things that I'm excited about thinking about within the context of sequential decision analytics is actually mapping decisions also into this kind of matrix to help think through how to solve problems more efficiently.
By the way, I think of rules-based as being ad hoc.
Okay, please say more.
The problem is, I know what you're trying to say, is that there's a lot of people who just can't articulate how they make a decision.
The rules.
They just can't tell you how they do it. And welcome to the human being.
We have a few questions coming in from the audience. And then, Kara, I'm going to come back to you to see if we can pull out some specifics about the client's engagement that gave you night shivers. But from Teresa, who's a friend of mine, question for Professor Powell. I'm currently a CS PhD candidate working as a data scientist with a background in software engineering. What steps would you suggest for someone with my background who is interested in exploring applied research in sequential decision analytics?
Simple answer, jungle.princeton.edu.
There you go. It couldn't be more simple. Couldn't be more simple than that, Teresa.
But the two books that I showed you on the Jungle website are both of those books.
Yeah.
The undergrad book, look for OR 411. There's the grad book. It's the bullet right below it. Start with the undergrad book. Start with the book. It's an online book, Sequential Decision Analytics and Modeling. It's rough. I wrote it quickly. I used it once in a course. As soon as I finish my big book, I'm going to go back to refine it. But it's a good starting point. Because most of the chapters are examples. And by the way, if you take tinyurl / sequential decision analytics and then put PUB at the very end for public, that's another online book, but you can write your own chapters. And I would challenge you to take a problem and take the same style and write your own chapter.
Interesting.
It's education.
And then there's a question from Jocham, who says, is it a question or a comment? So Jocham says, in my view, one of the first challenges is to help people that make supply chain decisions to understand the impact or consequences of their decisions. What are your thoughts about creating decision support insights that help people?
Sure, that's a great question, because at the end of the day, some of the most important decisions are still going to be made by a computer. Lisa, if I was going to help Lisa, at the end of the day, I'm not going to tell her where to open her next facility. I'm going to give her numbers, but what the computer is really good at is doing the little micro simulations, the little fine details that roll up that allow her to make a decision, where the simple fact is you can quantify some things and sometimes you just can't. Sometimes things are messy. I see her nodding, because facility location is a nightmare. I mean, it's a whole academic field. I don't know if anybody uses those tools, because locating a facility is just, at the end of the day, it's messy.
Yeah.
So sometimes but what you can use is use a computer to do the more detailed modeling and running many scenarios, so that you understand all the different possibilities, because the world is not a deterministic future, and I can use a computer to run 20 or 100 scenarios and then get probabilities on what might happen, and that informs a decision maker, likely so on a complicated problem like that. So I think we can have, on some of the more higher level, especially strategic decisions, I think a computer should guide a human. As you get to the more operational stuff that's every day, the more frequent it gets, the more you're like, I honestly think the computer should be making this decision. I think where optimal dynamics is heading, we're really focusing on a lot of operational decisions. And I have I think most of the stuff we're helping with is going to be something where the computer ends up making the decision. I mean, we'll have a few edge cases, but
yeah.
Since you were talking about me, I wanted to jump in here. Warren, thank you so much for mentioning refashioned OS. The very first level of decisions absolutely is location, 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 and making sure we find one where, you know, there's a density of seamstresses that have the right skills, and that there's repair people for the type of heavy electronics and hardware we're going to have, and all the things that go into site location. But the reality is, the future of all supply chains, and especially ones like refashioned OS, they're an interconnected network of constant daily minute decisions that lead to you know, this massive data set, and it's something that any human would go crazy having to keep track of. So the only way to manage, you know, which textiles we're going to need on what replenishment cycle to distribute to each of the micro factories across a region, to meet the demand for certain types of production and units being delivered within each region. There's so many of those decisions that just need to be done by a machine.
Yeah.
By the way, in your facility location, I can't wait to get you to draw on a sheet of paper all the various growth paths that might happen with your company. Okay? Go out 3 years and give me all the various trajectories. I need to challenge you to think about the uncertain growth of your company, because I have a feeling quite wide.
Yep.
Walk that back, because you'll start to find that that's a little bit overwhelming. Because there are many, many trajectories, but you have to make a decision now. Those facilities don't just pop up in a day.
Yep.
It takes some time.
We've got some complex models already in development to walk you through those, Warren.
Kara, let's talk about a past engagement that you and the team at RRDS Chicago have worked on, where in hindsight, if, you know, this framework existed at the time and you knew how to implement it, it might have, you know, we can't say for sure, but it might have led to a better outcome.
Yeah, you know, in hindsight, I think we were kind of stumbling around this because it was the only way to break it down and figure this out. But it's not what we were calling it. So it was a consumer packaged good problem, thinking about allocating marketing resources and figuring out, you know, they had these distribution partners, 3 distribution partners with different models. And so they were trying to figure out, like, how do we actually allocate spend among these distribution providers who would actually go and put the products on shelf. And so there are 3 things to kind of think about and control for. So on shelf availability, right? So at any point given the year, you could have like July 4th weekend, maybe hot dogs and ketchup are more popular. And so that's why you're more likely to be out of stock versus the week after. So controlling for all these kinds of things, controlling for regional differences, you know, why certain products do better in certain regions than others. And that explains why you need more product on the shelf here versus someplace else. Then the distribution piece, you know, the different distribution providers would visit the stores different amounts of time, and they would have different amounts of control with the managers of the store. So controlling for that. And then finally, this display piece, which talked about, you know, are there coupons on offer? Are there like special displays like at the end of the aisle that impact how people are buying? So at the end of the day, of course, you want to maximize the revenue by product, given the amount of money you can spend across these different distribution providers. So that was the problem that we were working on.
Warren, thoughts, comments, observations?
Yeah, so let's face it, these supply chain problems are complex. There's a lot of dimensions to them. Lisa had a nice example of like, okay, to locate that facility, you have to think about how many seamstresses are in the area, and you may not actually have data. And even if you had data, not really sure a computer would do a great job with things like that. One of my early transportation projects in LTL trucking, they were using our big network model to figure out where to put a break bulk facility. And we kept coming up with this location where the industrial engineers would go, oh my God, yeah, but the unions. Can't locate it there. Maybrook, New York. Don't go near Maybrook. You know? And some of these issues aren't that well handled by computers. But I still think that the exercise of trying to say, what would it take to have a computer make this decision? I think it's a good exercise, because the computer, you'll be able to say, look, this is the stuff that we're just not very good at quantifying. In a lot of our models at Optimal Dynamics, we have to put bonuses and penalties to encourage behaviors just because they're saying, look, I need to get drivers home this often. I need to provide this level of service. Well, why is that? Well, you know, let's face it, it's just a subjective judgment. But the exercise of thinking through, yes, but let's boil it down to the decisions and the metrics and then the uncertainties. Lisa, you got to think about your uncertainties.
And I'm thinking about Kara's bio, where she says she's the analytics translator. It sounds like she now has an additional tool to
let me say
add to her toolbox.
Well, I just wanted to also say just that, you know, so when we worked on this problem, because it was so complex, we had to get to the level of approximations. And that's what we did. We, you know, broke down each of these various components and tried to think about the contribution. And so that's why I said, I think we kind of stumbled into this because we were like, oh boy, right, exactly. But now I feel like this formalizes what we kind of intuited, like how to break down the problem. So we did, you know, diff and diff regressions, you know, tried to figure out, are there baselines we can look at to create control environments, conducting simulated experiments to see, you know, is this behaving the way that we hypothesized, you know, putting all these things together. But I feel like what Professor Powell has laid out kind of formalizes all of that.
Now, let me also emphasize that even though I am biased on the analytics, because at the end of the day, I'm all about, I want to find decisions I can put on the computer, that what's the decision question and what are the metrics, things like that. That's not analytical. Okay. And so if I was going to say, look, I really need a degree that teaches people with broad-based skills, I really had this vision of like an industrial engineering / management degree. Northwestern has an MMM degree where they combine the skills. And you actually do need people who maybe don't have analytic skills at all, but they do have that ability to go in and peel apart an organization, but they have to know what questions to ask.
Right.
Okay, so they have to be trained in the questions, like what's a decision? It's amazing how many people don't always recognize what's a decision. So I was talking to a data scientist at a logistics company, and he insisted something was a decision. And I'm like, no, that's not a decision. That's something you're estimating. It's the decision always has to imply a choice, that you have a choice. I can do this or this. If you don't have a choice, it's not a decision.
It's not a decision.
Okay. And so understand, like I remember doing, I was invited to the, Amazon did a first workshop for academics. And they gave us a tour of their local fulfillment center. And I just, as a little private exercise, went around looking for decisions. And I would be writing down. So they were sitting there wrapping up this really messy lamp. And I'm like, that's a decision. They didn't have to sell that lamp. Yeah. And that lamp just didn't fit their system of boxes. And so they had to have a human custom wrapping this lamp. And I'm like, that just doesn't work.
That doesn't work. Yeah.
So,
You know, what's kind of interesting is that, you know, sometimes you would assume also that technical people, like engineers, would intuitively understand some of these problems. But we've come across cases where, you know, sometimes engineers, like we have to explain, like, you know, different levels of data, you know, for a classification problem, why it's important to have, you know, a unified level of data. And it's like, you get so much pushback. So you can't automatically assume that just because somebody has a, you know, quote unquote technical background, or, you know, that they are going to think through these things in a systematic way.
We're going to come back. We're going to come back to this issue about backgrounds. Dirk, I want you to get ready because I'm going to come back to you to like talk a little bit more about an example that you've encountered, and we'll get the professor's comments. But before that, Charles Beckwith is asking, Professor Powell, would you please address potential strategies for using data to move, and he's worried about entrenched thinking by longtime executives and bureaucrats who are comfortable with the status quo. How do you talk to people about this where they're worried that this is magic and that it's all unsubstantiated?
let me tell you what I'm going to pitch. Sorry, I'm going to tell you what we do at Optimal Dynamics.
Yeah. Please go for it.
It took us a number of years. We built a very detailed simulator so that we can bring in the company's data and say, here's A versus B, and here's how much money we're going to save you. Okay. Now, the challenge there is we've built a simulator flexible enough that we can simulate virtually any truckload carrier. Now, I think a nice challenge is to do the same thing for supply chains. And then you can do what if on the company's data, because I'll tell you what changes opinions really quickly. It was when we come back and we go, okay, yeah, we can impact your bottom line by about $20 million. Yes or no? And let me put it this way, that's going pretty well. The thing is, it's a very credible simulator. We did a lot of work to make sure that this is realistic.
Yeah.
Now, you're going to have companies where, I mean, if you can't do that, then the fact is you're just a guy waving his hands saying, trust me, there are no shortage of very, very accomplished academics who are very smart and, the most dangerous of all, very good salespeople. And they're wrong. I'm sorry. I can tell you they're wrong. You know, they don't know what they're talking about. They're not going to have any benefit. They believe they will. They have good intentions. And so some of these skeptical managers, it's okay to be skeptical.
It's okay to be skeptical.
I think having the tools that really show you that it's right. The thing is, at the end of the day, at some point, if you really have a better mousetrap, industry has a good way of figuring out whether that's right. You'll always have the early adopters, and if it works for them, they may be the winners. And the people who aren't adopting, they just go out of business. So if you're stuck at a company, which is very reluctant, you know, if they have market presence that says they're not going to go away, fine, but they won't grow very much. I mean, I've seen companies, I can name one, I won't go into any details, where they absolutely think their stock price should be worth much more, but they're not willing to do the really fundamental change to get that big number. And so this is a problem. The thing is, one nice thing about being in the tech sector is we just choose not to work with those companies. Mostly they don't choose to work with us. The wonderful thing is the tech sector, and this is where, I'm sorry, I do believe sometimes being an outsider, Kara, you're a consultant, sometimes you have to be that outsider.
But I come from a tech background. You know, I studied applied math, and, you know, I was an algo trader for many years. So I code and do statistics. And so I'm an inside outsider. So Charles, I just wanted to jump in and say, Charles, like, honestly, like, please, like, I've spent so much time thinking about this problem because we have done so many, 6- and 7-figure projects where we develop beautiful models and then there's no buy-in. And so that's what inspired us to develop this MODO framework, which really talks about how do you actually set up your data science initiatives for success within your organization. So we look at mission mapping, we look at what is the overall mission within the company and how does the analytic that you're thinking about developing fit into the mission, because if there's a mismatch, you're not going to get buy-in. We look at objectives and commitments. Have you gotten the buy-in from the people, for resources in terms of time and money, to actually do these things? Have you looked at the toolkit that's available and identified, what's available in terms of hardware, software, data, processes, expertise, and knowledge? You have a way to capture all these things. And then finally, how do you define an optimal path out of that? And it's within the framework of all of these discussions that then we actually do the analytics. And then after you've gone through all this hard work, this philosophical work in a way, then you're in a much better position to actually see your initiatives succeed. So I'll just end with this. On my LinkedIn page, I have the MODO framework laid out and also a list of questions within the PDF that's available on my LinkedIn. And these are some of the questions that we routinely go through, like when we're starting a new project, to make sure that there's alignment and that there's an understanding. Because sometimes I feel like there is this kind of, magical thinking around like what can data science accomplish? And so going through these questions really grounds that understanding, I think, tremendously. So I'm finished.
I can make one comment. I want to emphasize two soft dimensions of analytics. One is the initial, what is the problem?
Yes.
Very, very important. Not easy. You need to be well trained, but it's not just technical. Okay. I'm sorry. You need business skills and the knowledge of the industry. The other is change management. Carrie, you were sort of hinting at that, or Charles, where once you've built the tool, you have to understand what does it mean to change the organization. One of the things that I did as a predecessor, Optimal Dynamics is standing on the shoulders of a lot of my failures. Early days, we were absolutely convinced that the way to optimize trucking companies is to find the best driver to move a load. And it took us a while to realize that wasn't the interesting question. And so Optimal Dynamics comes in. We've done a much better job of saying, this is the right question. It's easier to implement. We can have a bigger impact. Whereas I spent 20 years thinking, oh, no, I got to get rid of that room full of dispatchers. They're not very good at assigning the right driver to the right load. So finding those questions that are really the soft point, that's tricky. And then you have to understand, what does it mean to implement a tool? Okay, because I've seen companies where they'll say, oh, here's the data analytics guy. Let's see if their tool helps my room full of dispatchers. And then so they build a great tool and the room full of dispatchers sit there and go, well, I don't know.
We're not going. Dirk, so I remember you talking to us about, commodity shipping to Nigeria. And I remember that because, like I told you, I grew up in Nigeria. My parents still live in Nigeria. Completely blew my mind. But maybe you can walk through, if not that example, but some other example where in hindsight, if you knew this framework or had this to work with, your life would have been. There would have been there would have been a little less gray in your beard.
Well, I think both Warren and Kara, you call out a very hard point, but also a very correct point, asking the right question. So I noticed that with a different mindset, wanting to understand the context of things, instead of just how do I solve something, that actually led to a different line of questioning when I engage with traders, with supply chain managers, or execution people, or contracting desks, whatever, whatever you have within the field. Even if you talk about structured finance, so how does a contract, and why do you apply to this flow and not to that flow, and so on. This line of questioning is actually not taught in any BA level school. So it takes a lot of doubt. I'm afraid I have to use the word doubt, because you have to doubt what people say. It's kind of weird of saying, but a very simple example, when we talk freight, you might think, okay, that's the stuff that goes onto something to travel, right? In shipping, it's the freight I sell. So I'm selling you that I'm going to move your stuff. So imagine a discussion between two people. One is selling freight, one is buying freight, two different types of freight. And then there's a consultant in the middle trying to make heads or tails. You know, those two specialists know exactly what they're talking about. The consultant is like, okay, it's the same freight. Yes, good. Check that box. It'll be done. That's how you come to really weird outcomes in process design, in systems, and so on. The assumptions that they're made on the back of that, horrible. They're just, so it takes a very inquisitive and doubting mind to find the correct question. And you have to be really good at semantics. It's all people. So people give the answers. There's no screen telling you, oh, it's this. No way. So I think that also goes to the, if you want to apply this correctly and you say you have to find the right decisions to put into your system, you also have to find the decisions that nobody talks about. You know, they just go without saying. And what I used to do, for example, I would just have all those 8 people from beginning to end in a room, and I'd start drawing just little characters. So you're this guy, okay, yeah, you have a phone. Oh, you do this, and then I'd draw a contract or something else, and it would take me half a day, and then usually when you finish, they say, I actually didn't know that we do all those decisions. It's a very simple thing. The unaware, that they're completely unaware of what's going on. Now, your ask was, can you give me an example? In the supply chains of the commodity world that I'm living in currently, there are many factors. You already pointed out some interesting ones. You know, if it's cross-border trade and it goes into different currencies, that's an issue always. If it goes into territories where you might find less willingness to finance, that's a banking or fintech type of issue. So you're facing that as well. When you're hitting high seas, indeed the weather, but also the performance of a vessel, and has it been painted or cleaned recently, that has a huge impact on the fuel usage. And nowadays also something that has entered the field is, what's your carbon footprint? Is somebody willing to pay for a better performing vessel than for another type of vessel? So those are all kinds of decisions which are actually not known at the moment that you make your freight contract. Or for the customer, when he has the idea, okay, I think those sets of customers, I will deliver the one in April, the other one will be in October, and I'll do a shipment in the medium term for someone else, and so on. Had they known more about what's going on in the market, they might have made a completely different choice. So the sequence of their decisions actually kind of predetermines what they do, and it never changes, irrespective of what happens, unless they come up to that point in that moving month and they say, oh crap, this has really changed. I need to have a different freight contract, which doesn't happen. A simpler example is, we're talking about live products here. So by live, I mean they come off the land, they have a certain set of attributes, and those attributes might change over time. So if you put grains or beans on a truck, or you put them first into a bin and then into a truck and then again into a bin, they get handled and so on. So some might get damaged, but also contaminants might enter. They might dry or might get wet because it rains, during travel. Then there's the whole, we try to be good suppliers and we always manage, but if one of your customers has ordered a certain set of attributes that go with the commodity, and all of a sudden what you had expected coming in is completely different, on the spot you have to change an entire set of decisions that affect the entire supply chain. And to give you an example, in Poland or in Romania, there are about 15 to 20,000 truck movements just on our end. And that's just a tiny part of the industry. So imagine the snowball effect in the entire supply chain. They're humongous.
Dirk, is that during a day, during a month? What's the time frame? The truck
time frame is a month. So in a month, you kind of agree. We execute in a certain month, and then the recipient says, okay, better end of the month, or second half, or sometimes even a day. And that changes tremendously. And we have those contracts, CFA, CPA, or X works, whatever you choose. You take your goods delivered. If they don't deliver, what do? You can be mad. You can have all kinds of fines in your contract, which don't work because they don't solve your actual problem on the day.
Yeah.
How do you make a new solution? And that's when all the historical mapping in machine learning, I kind of distrust. They don't come up with the right solution to that daily problem. And that's where I like more what you're approaching here. That applies, well, it kind of conforms to my, as you know, I'm not a developer. I'm also not a mathematician. I just, through questioning what people do, came to the conclusion, it's more about the decisions that they make than that the flows that are moving at that moment that you plan, 6 months ahead of time. Those will happen. It's about those that don't happen that you have a problem with.
Yeah. Warren, thoughts, comments?
Well, it's obviously a rich area. When Dirk started listing all the things he had to think about just to get a load of agricultural commodities into Nigeria. Oh my God, I'm going to throw these up on that decision tree. And by the way, normally decision trees are making the same decision over and over again. I had to layer the decision, all the different types of decisions. But I think it still helps to list them all out and then list out the types of uncertainties. I mean, I'm sorry, there is still a process that you have to go through that I think, it seems complicated, but when you break it down, there's a process.
Yeah.
Okay. And I tend to find that you have to understand, it's not like I've always known how to do this my entire life. You should have seen me in the early part of my career when I spent 2 decades working on a truckload problem where I knew that I didn't know how to write it down on a sheet of paper. And here I am in academia where the only way I move forward is by publishing. Fortunately, nobody else in my community knew anything either. And as soon as they saw a paper with stochastics and optimization, like, oh my God, this is so complicated. I would say that 40 years later, the community hasn't moved very far. It's not much better. And I started to understand my aha moment of why we're in this case. But at a minimum, I do think that there is value in it, even if you're not going to write code and do a lot of math and have algorithms for this. Understanding the framework allows you to ask the right questions. And so anytime I sit there, I know what I want to ask. I know what I'm listening for. I know where it's going to go. I wish I had this when I was 40 years ago. Oh man.
Well, we have it now, so at least we can be happy with that. There's a question from my friend Jason, and I'll give Jason a shout out. He's a Connecticut College grad like I am, although he's much younger, much more good looking, and in better shape. But his question is, he says he's really enjoying and Jason works at the LA area Chamber of Commerce. So Jason says, I'm really enjoying the discussion. He's curious about how one might think about decisions made outside the company, but that impact the company directly or even an industry. And so in other words, for example, geopolitical types of things where the government has made a decision, how are the decisions made? I think that's a jibe at the government. And then he says, but how do you integrate that sort of thing into the decisions that you make within the company? And he gives an example. For example, in California, I guess they've decided to go fully electric in terms of trucking by 2035. And this is open to any one of you who has the courage, to tackle it.
I will tell you, one form of exogenous uncertainty is political decisions.
Yeah.
Okay. Now, uncertainties come in different flavors. I mean, and in different timescales. Okay. You have the little randomness and the prices bouncing up and down, and then you have, will they pass this new regulation as a major source of uncertainty? And you're like, okay, will the law pass or not? Yeah. If it does pass, will they change it back? Mm-hmm. If the Republicans get back in and just roll back. So political uncertainties and regulatory uncertainties is really problematic because tends to be a big source of uncertainty. And whether you're on path A versus path B can dramatically change things. And so that's the point at which you're saying, can I hedge?
Dirk or Kara, thoughts?
I was just going to, I was just going to add that like a Bayesian kind of approach can be helpful to think through as well, where you have, kind of a sense of, like an initial belief about how things are going to impact your model, and then you're like updating as you get more information.
Yeah.
Right.
Yeah, I would second that. And that is actually from another perspective. Look at the world we're also in, which is startups. How do you battle uncertainty? By taking little steps. Doesn't make you take 0 steps. It just makes you break it down into those essential points and try to take those little steps. And that's just what Kara said.
One idea is ask Lisa, because she's doing it.
And there's another question. There are 2 more questions, and then there's one that I had in mind. So David, David Cantor, who is at Mercer, and I'm going to give David a shout out. David is an actuary. So when I graduated from college, my first plan was to become an actuary, right? Like, what could be better than working and then going home to study math to take exams? Until I run into the exams and I realized, oh, those exams. But David is an actuary, and he says, as an actuary, we run simulations all the time to inform our decisions. 2 issues come to mind. One is information overload, and the second is model risk. That's very true. And he asks, any insights on that? For example, in finance, we can map simulations to utility functions and then try to get optimal decisions. Otherwise, we have tons of scenarios and probabilities associated with them, but it's hard to process unless there are slam dunk patterns. Thoughts?
Well, so what he's saying is that there's some settings where, I'm sorry, it really is uncertain.
Yeah.
You absolutely just don't know where it's going to go. You're going to have to live with the fact that you may have a bad outcome with a certain probability. Yeah. The slam dunk means that they kind of know what's going to happen.
They kind of know what's, yeah.
The problem is, sorry, you just sometimes don't.
Yeah.
So the thing is, the finance people will be asking, how do you hedge? Is there a way to hedge?
Right.
I'm sorry, somebody else was.
Yeah, Kara was. I was actually going to ask Kara because she's done work in financial services. Yeah.
I was going to say that we've actually used some Bayesian modeling in finance in particular to handle these kinds of questions. And then I would say the model risk is really huge. I mean, we talked a little bit about parameters, but I feel like the risk that you run into with parameter tuning can really get you into so much trouble. Where you develop models that look like they are robust and good, and then they fall apart in a minute. So I think I would say definitely the simulation piece, simulating under lots of different scenarios, I think helps to reduce some of the risk that you've perhaps overtuned things.
And one thing I try to Dirk, just one comment, and then I'll let you chime in on this. One thing I try to convey to my students at NYU during the spring 2020 semester is this idea that even those who wanted to go into finance and who thought, hey, I'm going to go into trading or banking or whatnot, really financial outcomes are a reflection of what's happening in the real world. And so that way of thinking about risk, that you can't just think about what's the risk based on my financial data, but you also have to attempt to understand the risk in the real world and how that shows up in the data that the finance people are living with every day. Dirk, do you want to take a swing at that question? And it's okay to say it's okay to say no if you want.
Yeah, no, well, I kind of agree with Warren. So one of the things that I find interesting, I explained in the bullet points when you asked me, so what would be the elements that I can share about you? And that's my fascination with uncertainty and how people respond under that.
Yeah.
And you know, the gambler's fallacy and all those kind of things, they're perfect because you trip over them yourself without noticing.
Without noticing.
And you know, one of the questions was, how do you, for instance, convey this to your leadership when they're so stuck in believing, well, this is how we run, and actually that's kind of fine, because if I look at the history, I've been right. So it kind of proves my point. So you get in this self-referential loop. You can't get out of it. And to me, that somehow also relates to, you know, Nassim Taleb's book on the Black Swan. So how do you know in a Mandelbrot set where you are? You know, you can get lost. And how do you then switch those people out of it? And sometimes I know it's completely wrong, but it helps them realize that they are thinking in circles. Is so imagine everybody's optimizing, and we're optimizing, and we're optimizing, and we're looking, we're starting to look like those high frequency traders. You know, we make microsecond decisions and so on, just based on the little information we get before everybody else does. Everybody else is doing the same thing. So what happens then? And I think we shared some exchanges on that. It somehow seems that the variance goes, and we need an amplitude in the market to something to happen. So it's not the object of flatlining everything. The objective is to serve better on those waves that are there. And that is a challenge you can give to your leadership. You know, imagine everybody does this and it's flatlined. What's your job then? Exactly.
That's uninteresting. That's uninteresting.
Slam dunk. Yeah, I think also though, I think this is perhaps where like small pilot projects come into play, right? Where you can find quick wins, where you can start to change minds, win hearts, you know, the soft side, you know, getting people over to your team. And so that's why it's so incredibly important to know the decisions that you can model well so that you actually have a positive outcome.
There's one more question, and then the one that but this is from the audience. So Anna works at a corporate VC for a consumer packaged goods company. I think the largest one in Mexico and LATAM, either the largest or the second largest. It's pretty big. I can't remember off the top of my head. But she says one of the biggest challenges for tech startups in early stages is what data to track, when to start, and how often to change those items that they're tracking to make decisions. How does one establish the basis on what is the good data that they should have for a decision process, especially if one is looking to head in the direction of sequential decision analytics?
Okay, so first of all, a quick thing. There's a decision right there in that question, is which data to track. That's a decision.
That's a decision, yeah.
If you have a sequential decision problem, you have a sequential decision problem. It doesn't matter whether you can solve it or whatnot. If you have a decision that you're making, such as what data to track, but presumably behind this, there's some physical, there's something physical going on. And you know, like Lisa's company, or an inventory problem, or even a tech startup that has to decide what product to take to market. These are all decisions.
So
what you have a sequential decision problem. So now the question is, are we going to use analytics to actually solve the decision problem? And I usually use my criteria for should we use analytics to actually solve it, because sometimes you use analytics just to think about it, and I think that's fine. Do we actually want to put together a computer model and go to that work? And this is where you have to look at the metrics and say, if I make a better decision, would I notice? Okay, I don't like one-time decisions, because whether you make them right or not, it's a one-time decision.
It's a one-time, yeah.
And I know that there's analytics there. People do decision trees for one-time decisions. I find them a little less interesting. I like the decisions that you're making during the day, every day, once a week, whatever. It's a regular decision that as you make it better, you'll notice, you can measure it. I mean, I would have students as an exercise, I send them to a Google spreadsheet when they were doing their summer internships and identify a decision. And sometimes they'd have a decision what restaurant to go to or what job to take or who to marry. And I'm like, you know,
Who to marry?
quantifiable, so that if you do better decisions, when you do them over and over again, you can notice whether you're making a better decision. And if you don't have that, then I'm like, okay, use the framework to think about your problem, but don't spend the time writing the code. I mean, optimal dynamics, we have to focus on the decisions where we have real economic value. Kara, you have a...
Yes, Kara has.
Yes, I put my pen up to say something. I was just going to say that I feel like this is a place where you can think about your strategic objectives also, like from a top-down approach. Think about what are the KPIs that are important for the startup, and then work backwards. Like what are to help identify the decisions that are important. I think it's helpful to have that, that higher level thinking around, okay, great, where are our goals? And what's going to move the needle, and where are competitors, and just going through that whole, like at a more strategic level, I think can drive your thinking about, okay, great, go through the process. Now this is the kind of data, this is the frequency at which we need it, because that's another place where people often kind of fall into a trap. Maybe the tempo at which they're collecting data isn't quite right. So that's also very important to consider.
Yeah.
So, yeah, I can second that. It's about the level of, let's say, resolution. In the beginning, you just don't know enough what choice to make. So at least start with one, and then add another one. And as you move forwards, you get to know more and start to ask, like Warren says, better questions. And then you apply better metrics. So it's always nice. I have this discussion with project managers. So they mistakenly see, hey, you're going to build a new company. Nice. I'll put it into a project. Well, I don't know what this company is going to do and if it's going to make money and who's going to run it and who the customers are. How certain are you that it's going to fit your project? Well, I've done this before, so it's going to fit. So, that's the misinterpretation. I know how projects run with, and applying that same type of, certainty to the underlying thing, and it's not going to happen. And then caution, take the Bayesian approach, do it in little steps. And
I was hoping we'd get to this question before Lisa had to leave, but she just left a comment that she has to jump, so she wouldn't get to chime in on it. But the idea of the sorts of human capital or people that we need in teams at companies, especially large companies, to tackle these sorts of issues, right? So there's the engineers, Warren, you talked about them. There's the business school people, the MBAs, and if Lisa were here, she'd say we also need the design and systems thinking people as part of those sorts of teams. And so I just thought we could talk about that a little bit for those who are still here, for the balance of our conversation. Just touch on that a little bit.
End users. How many projects have I had derailed because we didn't have the conversations with the end users, right? And so these are sometimes, the people who are going to be using the analytic in the field, right? So they should be brought in early. I would say that. And then, I'll make a pitch for this concept of like citizen data science. Now, it can be a little bit dangerous because sometimes like you just give like a bunch of access to data to people who don't necessarily have like, good sensibility about modeling and, what constitutes a good model, et cetera. But I think opening the floor and getting people's comfort level, people who are in the trenches every day actually working on problems around, hey, like this is the data we're looking at, and let's actually see if we can come up with something new or novel. I feel like within organizations that are able to have like pull data science out of like a siloed function and have it be across the organization, and now everyone is kind of participating and thinking about how could we apply data to this decision or this problem. Those are the companies that are most innovative.
It's I completely understand what you mean. When we were starting out to build the Worldwide Supply Chain Federation, but specifically the meetup, the New York Supply Chain meetup, and we said we're going to take a broad tent approach. So it's literally the qualifier is, do you have an interest in supply chain innovation and technology, whatever your background? If the answer is yes, we want you. And people were like, but that's going to be so difficult and messy. And I said, but that's how we're going to find the ideas that are completely from left field, that no one who's in supply chain, whether they're academic or professional or in industry or in technology, has thought about, right? Someone will ask a really simple, fundamental, basic question. And that's what gets and I just thought, my argument was, I think that's where the disruption comes from. But yes, it's been. If you see any gray hairs on my head, that's part of Dirk.
Yeah. No, I totally agree. So I have in my signature in my email a small line that I thought of. I don't know, when I started at Cargill could be. It says, if you keep doing what you did, you end up where you are.
Yeah.
So you need to really, and I think that is not so broadly taught within the universities, at least that I know here in Europe, and especially here in Holland and in Germany. You get taught methods. That's nice. If you know when to apply them, that can be very practical. But if you don't know why you're applying them, then there's a problem. And if you get stuck in one field, then you get used to applying a certain method. And well, kind of applies to what Warren said, you can go down deep into one subject, one piece of the puzzle. But if you don't have a cross-sectional awareness of why people are making decisions, so you can ask the right difficult follow-up question and so on, it kind of doesn't help. It is become quite complex if you need to be aware of everything at the same time. But if you teach yourself those basic concepts of what people are working with, it clarifies a whole bunch. So I'm all for it. Bring in different types of people, and like Kara said, it doesn't. You need to have a broader view than just that field that you're in.
Yeah. Thank you.
And I'm an architect, so I know.
Warren, thoughts? Closing thoughts.
Yeah, I think that what I'd like to think is that the idea of thinking through decision problems analytically adds some structure to what's a really complicated process. It's not going to solve all problems.
Yeah.
We still have a soft side of identifying what the problem is. There's a soft side of implementing solutions. And then I wish Lisa were here, because I will put a nod to the creative side, because let me tell you what a computer won't do. A computer would never have envisioned REFASHIOND OS. That whole vision had to come from a human brain. And that's sort of big thinking. The soft side of understanding a supply chain, because you may want to say, this is just the wrong way of doing it, we should do it differently. That's not going to come out of a computer. Computer's really good at sort of more of the micro stuff, simulating the details, quantifying uncertainty, making the best decision, simulating the little decisions while a human's making the big decisions. I think for my foreseeable future, looking at for a while, it's going to be very much of a hybrid process. I think it has to be more automated than it is now. But we do have to understand the limits. I mean, the computer scientists are fabulous at playing the game of Go. I'm sorry, the game of Go has really well-defined rules. Supply chains don't have. They do have a lot of things that are defined that you can model, and those are the things where we should go in and use computers for.
So are the Go rules ad hoc, Professor Powell?
The Go rules?
The rules.
No, because earlier you said, when I was talking about rules-based, and you said, I think all rules are ad hoc.
When you say ad hoc, remember, I've got my claim that I'm going to stand on, that everything fits in the grand framework. So when you say ad hoc, it's got to go in one of the boxes, and I'm pretty sure it's in the rule box. The hard part is articulating. See, the one difficulty that I've seen when a bunch of humans are making decisions is you don't always know how they're making decisions, and that's a bad thing. You know, I'm sorry, especially on things that are repeatable. When somebody says, well, you know, I have to decide whether to reject that load. Well, you're going to do that dozens of times during the day. Well, how do you think about that? Well, I don't know. Well, I sort of, you know, have some complicated thing. I mean, I remember my very, very early days of doing load matching. I would sit with people actually assigning drivers to loads, and every now and then they would say, I need a minute to solve a problem and do, I don't know, something that only I understand. They weren't being rude. They just, sometimes humans take over to do things. And I'm sorry, sometimes we humans can't even articulate what's going on in our own brain.
Yeah.
And that's not necessarily a good thing, but there is also a creative side. You know, when Toyota came up with, you know, their just-in-time stuff, sorry, that's not going to come out of a computer.
Yeah.
And so we just have to strike that balance. I mean, I love the story of Elon Musk, who said, no, we're going to just have robots doing everything. And by the way, we're going to run the robots about 10 times the rated speed.
Yeah.
Well, guess what? Robots are terrible at handling electricity harnesses. And Elon Musk has this great quote where at the end of the day, he realized humans are just better at some things.
Some things, yeah.
And that human hand is fabulous at reaching in and twisting and getting that electrical harness in under the seat, and robots are terrible.
Yeah, terrible at doing.
Let me tell you, the next thing that Elon Musk started to do was to say, let's get rid of the harness. Let's get rid of winding harnesses. In other words, Uber is a great example. You could have gone in and utterly automated the whole process of dispatching taxi cabs, or you could do what Uber did, which just says, let's just get rid of the whole process and start from scratch. To some extent, REFASHIOND OS is doing some of that.
Something, yeah, like that.
Instead of doing a better job at managing the inventory of garments, they're getting rid of the inventory. The whole process. So I think that's a great example of where that's what humans are fabulous at. Computers can help, but not that original.
Yeah.
All the people who think AI is going to replace humans, come on.
No, I think that's the important distinction between automation and just enrichment or augmentation, I guess, right? The areas where you can completely remove a person's interaction, and those areas where no matter what, you're going to need human decisions because the decisions are too costly or important, or you want that creative factor incorporated. So no, this has been a fantastic discussion.
I was just going to say I have a decision to make. We've been talking for more than the 2 hours that we budgeted, and we've lost most of the people in the process because obviously these are busy executives who have decisions to make in their jobs. But thank you very, very much for joining us for this. Everyone who has left a comment has said, super event, fantastic event. This is amazing, great event, and so on and so forth. I'm going to process the video and whatnot. I have to ask Lisa if she wants to put any flourishes to it before we publish, but then we'll put it online and I'll send the link to everyone who signed up. So once again, thank you very, very much. And here is to all of us making better decisions in the future.
Thank you. Thank you, Brian.
Thank you.
Absolutely.
Thank you.
Indeed.
Thank you.
Thank
Bye-bye.
you.
Bye-bye.
Bye.
Bye-bye.